In the distant reaches of our solar system, where Saturn reigns as the crown jewel of the outer planets, there exists a moon unlike any other in the known universe, Iapetus, named for the Titan of Greek mythology who fathered Prometheus and Atlas, has captivated human imagination since its discovery over 3.5 centuries ago. This mysterious world, sometimes called the yin-yang moon for its striking two-toned appearance, holds secrets that continue to puzzle scientists and inspire wonder in all who learn of its existence. Tonight, as you settle into comfort and let the weight of the day drift away, we shall journey together across nearly 900 million miles of space to explore every facet of this extraordinary celestial body. The story of Iapetus is one that spans centuries of human curiosity, from the flickering candlelight of 17th century observatories to the sophisticated instruments of modern spacecraft. It is a tale woven through with mystery, scientific discovery, and the endless human desire to understand the cosmos that surrounds us. In Greek mythology, Iapetus was one of the 12 Titans, the son of Uranus and Gaia, and the father of some of the most famous figures in ancient legend. His name, which some scholars believe means the piercer or the wounder, seems almost prophetically appropriate for a moon that has pierced through so many of our assumptions about how worlds form and evolve. The ancient Greeks could never have imagined that this name would one day belong to a distant moon orbiting the ringed planet. Yet here we are, centuries later, still finding meaning in those old stories as we apply them to new discoveries. What makes Iapetus so remarkable, what sets it apart from the hundreds of other moons in our solar system, is its profound strangeness. This is a world divided almost perfectly in half, with one hemisphere as dark as coal and the other as bright as freshly fallen snow. This is a moon with a mountain range running precisely along its equator, a feature so unusual that when scientists first saw detailed images of it, many refused to believe what they were seeing. This is a celestial body that orbits Saturn at such a great distance and at such a peculiar angle that it offers views of the ring system that no other major moon can provide. And this is a world that has inspired science fiction authors, sparked countless scientific debates, and reminded us again and again that the universe is far stranger and more wonderful than we could ever imagine. As we embark on this journey together, allow yourself to relax completely. Let your breathing slow and deepen. Feel the tension leaving your muscles as we drift through the darkness of space toward this enigmatic moon. There is no hurry here, no urgency. We have all the time we need to explore every crater, every mountain, every mystery that Iapetus holds. The universe has been patient for billions of years, and it will wait for us as we take this gentle voyage through its wonders. The darkness between the stars is not empty, but filled with a profound peace. As we travel outward from our own blue world, past the rust-coloured deserts of Mars, through the asteroid belt with its countless tumbling rocks, past mighty Jupiter with its swirling storms, we approach the realm of Saturn. And there, far from the famous rings that make Saturn so recognisable, orbits our destination. Iapetus awaits us, keeping its secrets close, ready to share them with those patient enough to listen. Let us begin at the beginning, with the moment when human eyes first glimpsed this distant world, and a mystery was born that would take centuries to unravel. The discovery. Giovanni Cassini and the birth of a mystery. The year was 1671, and in the Grand Observatory of Paris, a man named Giovanni Domenico Cassini was about to make a discovery that would puzzle astronomers for generations to come. Cassini, born in Italy, but now serving as the first director of the Paris Observatory, had already established himself as one of the finest astronomical observers of his age. He had discovered the great red spot on Jupiter, determined the rotational periods of Jupiter and Mars, and would eventually discover 4 of Saturn's moons. But on this particular night, as autumn settled over the French capital and the air grew crisp and clear, Cassini turned his telescope towards Saturn with a curiosity that would soon be rewarded in the most unexpected way. The telescope Cassini used was a marvel of 17th century engineering, though by modern standards it would seem almost impossibly crude. These early refracting telescopes suffered from chromatic aberration, producing coloured fringes around bright objects that made detailed observation challenging. To minimise this effect, astronomers built telescopes with extremely long focal lengths, sometimes stretching dozens of feet. Cassini's instruments were among the finest available, crafted by the skilled lens makers of the era, and on clear nights they could reveal details of the planets that no human eye had ever seen before. Saturn had long been a source of fascination and confusion for astronomers. When Galileo first observed it through his primitive telescope in 1610, he thought he saw a planet with 2 large companions on either side, describing Saturn as having ears. The true nature of Saturn's rings would not be understood until Christian Huygens proposed the ring theory in 1655. By Cassini's time, the rings were recognized for what they were, and astronomers were beginning to discover that Saturn, like Jupiter, possessed a family of moons. Huygens had discovered Titan, Saturn's largest moon, in 1655. This massive world, larger than the planet Mercury, was bright enough to be spotted with the telescopes of the day. But Cassini suspected there might be more moons waiting to be found, smaller and fainter, lurking in the darkness around the ringed planet. Night after night, he carefully mapped the positions of every point of light near Saturn, looking for any that moved in ways that would indicate they were moons rather than distant stars. On October 25th, 1671, Cassini noticed a faint point of light on the western side of Saturn. He carefully noted its position and continued his observations over the following nights. The point of light moved, clearly orbiting Saturn rather than remaining fixed like a background star. Cassini had discovered a new moon, one that would eventually bear the name Iapetus, though Cassini himself simply called it one of the Sidera Lodoicea, the stars of Louis, in honour of King Louis XIV of France, his patron. But something strange happened as Cassini continued to track his new discovery. The moon seemed to disappear. On the western side of Saturn, it was clearly visible through his telescope, but when it should have appeared on the eastern side of the planet, having completed half of its orbit, it was nowhere to be found. Cassini searched and searched, but the moon had seemingly vanished into the darkness of space. This was deeply puzzling. Moons do not simply disappear. They orbit their parent planets in predictable paths, governed by the same laws of gravity that keep the Earth circling the Sun. Yet here was a moon that could only be seen on one side of Saturn. Cassini, being the careful and methodical scientist that he was, considered various explanations. Perhaps the moon had an extremely elongated orbit that took it far from Saturn on one side. Perhaps there was some obstruction blocking his view. Perhaps his initial observations had been in error. But as months passed and Cassini continued his observations, a pattern emerged. The moon was always visible on the western side of Saturn, always invisible on the eastern side. It was as if the moon itself was somehow different depending on which side it was showing to Earth. And then, with a flash of insight that demonstrated his remarkable scientific intuition, Cassini proposed an explanation that would prove to be correct, though he could not have understood the full implications of what he was suggesting. Cassini hypothesized that Iapetus had one hemisphere that was much darker than the other. When the bright hemisphere faced Earth, the moon was visible. When the dark hemisphere faced Earth, the moon was too dim to be seen with the telescopes of the day. This explanation required that Iapetus, like our own moon, be tidally locked to its parent planet, always showing the same face to Saturn as it orbited. This was a reasonable assumption, as tidal locking was already understood to occur with close orbiting moons. What Cassini could not have known was just how extreme this brightness difference would turn out to be. He could not have imagined that one side of Iapetus would be as dark as charcoal, while the other gleamed like ice. He could not have predicted the centuries of scientific debate that would follow, as astronomers struggled to explain how such a dramatic difference could exist on a single world. And he certainly could not have foreseen the spacecraft that would one day bear his name, travelling across the solar system to photograph Iapetus in stunning detail and reveal mysteries even more profound than the one he had discovered. In the years following his initial discovery, Cassini continued to observe Iapetus whenever conditions permitted. He refined his measurements of its orbital period, determining that it took approximately 79 days to complete one circuit around Saturn. He noted that its orbit was significantly inclined relative to Saturn's equator and ring plane, a peculiarity that set it apart from most of Saturn's other major moons. And he continued to puzzle over the brightness variation, gathering more evidence to support his hypothesis of a two-toned surface. Cassini's discovery of Iapetus was just one of many contributions he made to our understanding of Saturn. He went on to discover 3 more Saturnian moons, Rhea in 1672 and Dione and Tethys in 1684. He also discovered the gap in Saturn's rings that now bears his name, the Cassini division, a dark band that separates the bright inner B ring from the outer A ring. His legacy in planetary astronomy is immense, and it is fitting that the spacecraft sent to study Saturn in the modern era was named in his honour. But of all Cassini's discoveries, Iapetus remained perhaps the most mysterious. The other moons he found were relatively normal, as moons go. They orbited in the plane of Saturn's rings. They had surfaces of relatively uniform brightness. They behaved as moons were expected to behave. Iapetus, with its extreme brightness variation and its tilted distant orbit, was something altogether different. It was a puzzle wrapped in an enigma, a world that seemed to defy easy explanation. As telescopes improved over the following centuries, astronomers were able to confirm and extend Cassini's observations. The brightness difference between the two hemispheres was measured more precisely, and it became clear that this was not a subtle variation, but an extreme one. The dark hemisphere, which astronomers would eventually name Cassini Regio in honour of the moon's discoverer, reflected only about 4% of the sunlight that struck it, making it one of the darkest surfaces in the solar system. The bright hemisphere, later named Roncevaux Terra, reflected nearly 60% of incoming light, making it one of the brightest. The contrast between these two regions was unlike anything seen on any other moon or planet. Various theories were proposed to explain this remarkable dichotomy. Some astronomers suggested that Iapetus had been painted by material from another moon, perhaps debris ejected from the dark, distant moon Phoebe by meteorite impacts. Others proposed that the dark material was organic compounds, similar to the tarry substances found on some asteroids. Still others wondered if volcanic activity might have coated one hemisphere with dark lava while leaving the other pristine. Each theory had its merits, but none could fully explain all the observations. The mystery of Iapetus deepened further when spectroscopic observations revealed that the dark material contained carbon-rich compounds, possibly including complex organic molecules. This raised intriguing questions about the chemistry of the outer solar system and the processes that might create such materials. Were these organics primordial, dating back to the formation of the solar system itself? Or had they been created more recently through chemical reactions driven by sunlight or radiation? As the 20th century progressed and the space age dawned, astronomers began to dream of sending spacecraft to the outer planets. planets. The grand tour opportunity of the late 1970s, when the outer planets would be aligned in a configuration that occurs only once every 175 years, offered a chance to visit Jupiter, Saturn, Uranus, and Neptune with a single spacecraft. The Voyager missions were born from this opportunity, and in 1980 and 1981, they would provide humanity's first close-up views of Iapetus. But before we journey forward to the space age, let us pause and appreciate the magnitude of what Giovanni Cassini accomplished on that autumn night in 1671. With nothing more than a glass lens and his own keen eyesight, he discovered a world that would puzzle scientists for more than 3 centuries. He correctly deduced the basic reason for its strange brightness variations, even though he could not have understood the complex processes responsible. And he added another chapter to humanity's ongoing exploration of the cosmos, a chapter that would eventually lead to robotic emissaries travelling across nearly 1 billion miles of space to photograph the very moon he had first glimpsed in the flickering candlelight of Paris. As you rest and relax, imagine yourself in that 17th century observatory. Feel the cold stone beneath your feet. See the candles guttering in the draught from the windows. Hear the scratch of quill on paper as observations are recorded. Above you, through the long tube of the telescope, a faint point of light marks the position of a world that no human had ever seen before. You are witnessing a moment of discovery, a moment when the boundaries of human knowledge expanded just a little bit further into the vast unknown. These moments are precious, and they connect us across the centuries to all those who have looked up at the night sky and wondered what mysteries might be waiting to be found. The story of Iapetus was just beginning on that October night in 1671. The centuries that followed would bring new telescopes, new theories, and eventually new spacecraft to continue the exploration that Cassini had started. But the fundamental mystery remained, tantalizing and unsolved, waiting for the technology and the determination that would finally allow us to see this strange moon up close and begin to understand its secrets. Chapter 2. The Two-Faced Moon and the Great Dichotomy. As we drift deeper into our exploration of Iapetus, we come to perhaps its most famous and visually striking characteristic, the feature that has earned it the nickname the yin-yang moon, and captured the imagination of scientists and dreamers alike. This is the Great Dichotomy, the dramatic division of Iapetus into 2 starkly contrasting hemispheres that makes it unlike any other world in our solar system. Picture, if you will, a sphere divided almost perfectly in half. On one side, a surface so dark that it absorbs nearly all the light that falls upon it, reflecting back only about 4% of incoming sunlight. This darkness is profound, deeper than fresh asphalt, darker than charcoal, approaching the blackness of a moonless night. This is Cassini Regio, named in honour of the astronomer who first glimpsed this moon more than 3 centuries ago. It sprawls across the leading hemisphere of Iapetus, the face that perpetually looks forward as the moon travels along its endless orbit around Saturn. On the opposite side lies a landscape of startling brightness. Here, the surface gleams with an albedo of nearly 60%, reflecting more than half of all sunlight that reaches it. This is Roncevaux Terra, a vast expanse of water ice so pure and so bright that it would dazzle your eyes if you could stand upon it. The name comes from the medieval French epic, the Song of Roland, connecting this distant, frozen world to the rich tradition of human storytelling that stretches back through the ages. The contrast between these 2 regions is so extreme that early observers could scarcely believe what their instruments were telling them. When the Voyager spacecraft sent back the first detailed images of Iapetus in the early 1980s, scientists stared at the photographs in wonder and confusion. How could a single world possess two faces so utterly different from one another? What cosmic processes could have painted one hemisphere with darkness while leaving the other pristine and bright? To understand this mystery, we must first appreciate the scale of what we are observing. Cassini Regio covers an area of approximately 4 million square miles, roughly equivalent to the entire continent of Europe. Within this vast dark province, the surface material is composed of complex carbon-rich compounds, organic molecules that have accumulated over billions of years. These are not the organics of life as we know it, but rather the building blocks from which life might someday emerge, or the remnants of chemical processes that occurred in the cold depths of the outer solar system long before Earth existed. The dark material is not uniformly distributed across Cassini Regio. In some areas, it forms a thick coating that completely obscures the underlying ice, creating landscapes of unrelieved darkness. In other regions, bright patches of ice peek through the dark veneer, suggesting that the coating is relatively thin in places, perhaps only a few feet deep. Impact craters within Cassini Regio often reveal bright flaws, where the impacting body punched through the dark layer to expose the ice beneath, providing direct evidence that the darkness is a surface phenomenon rather than a fundamental property of the Moon's interior. Roncevaux Terra presents an entirely different picture. Here, the surface is dominated by water ice in its most pristine form, ice that has remained largely uncontaminated by the dark materials that coat the opposite hemisphere. The brightness of this region is remarkable, exceeded in our solar system only by a handful of other icy bodies such as Saturn's moon Enceladus and some of the smaller satellites of Uranus. Walking across Roncevaux Terra would be like walking across a landscape of fresh snow under a brilliant sun, though the sun at Saturn's distance appears much smaller and dimmer than it does from Earth. The boundary between these two regions is not a sharp line, but rather a gradual transition zone where dark and bright materials intermingle in complex patterns. This transition zone holds crucial clues about the processes that created the dichotomy and continue to shape it today. In some places, fingers of darkness extend into the bright terrain, following the contours of valleys and crater floors. In others, islands of brightness persist within the dark region, suggesting that local topography can influence the distribution of surface materials. For many years, scientists debated the origin of this remarkable feature. Some proposed that the dark material was endogenic, meaning it originated from within Iapetus itself, perhaps through volcanic eruptions or the exposure of subsurface materials. Others suggested that the darkness was exogenic, deposited on the surface from external sources. Still others wondered if some combination of internal and external processes might be responsible. The breakthrough in understanding came with the discovery of the Phoebe ring in 2009. This enormous, diffuse ring of dark material orbits Saturn at a great distance, tilted at an angle that matches the orbit of the small dark moon Phoebe. The ring is composed of particles knocked off Phoebe's surface by micrometeorite impacts, particles that slowly spiral inward towards Saturn under the influence of various forces. As these particles drift inward, they encounter Iapetus, which sweeps through the inner edge of the ring like a cosmic vacuum cleaner. The geometry of this encounter is crucial to understanding the dichotomy. Because Iapetus always keeps the same face pointed towards Saturn, and because it orbits in the same direction as most of Saturn's other moons, while the Phoebe ring particles drift in the opposite direction, the leading hemisphere of Iapetus receives the bulk of the incoming dark material. Over millions of years, this steady bombardment has coated the leading hemisphere with a layer of Phoebe-derived particles, creating the basic pattern of the dichotomy. But the external deposition of dark material is only part of the story. If this were the only process at work, we would expect to see a gradual variation in darkness across the surface, with the leading hemisphere being darkest and the brightness increasing smoothly toward the trailing hemisphere. Instead, we observe a much sharper contrast, with very dark and very bright regions existing in close proximity. Something else must be amplifying and sharpening the dichotomy. That something else is thermal segregation, a process that exploits the different heat-absorbing properties of dark and bright materials to redistribute ice across the surface of Iapetus. The dark material absorbs more sunlight than the surrounding ice, causing it to warm up. This warmth drives the sublimation of water ice, the direct transformation from solid to gas that occurs even at the extremely low temperatures found in the outer solar system. The water vapour released by sublimation does not escape into space, but rather migrates across the surface, eventually refreezing in colder, brighter regions. This process creates a powerful feedback loop. As ice sublimates from the dark regions, the dark coating becomes more concentrated, making the surface even darker and warmer. This drives more sublimation, which further concentrates the dark material, which drives still more sublimation. Over millions of years, this runaway process has stripped most of the ice from the leading hemisphere, leaving behind the thick, dark coating we observe today. Meanwhile, the water vapour that migrates to the trailing hemisphere refreezes there, adding to the bright ice deposits and keeping that region cold and reflective. The evidence for thermal segregation is compelling. Temperature measurements from the Cassini spacecraft confirm that the dark regions are significantly warmer than the bright regions, exactly as the model predicts. The distribution of dark and bright materials matches the patterns expected from thermal migration, with the darkest areas concentrated near the equator, where temperatures are highest, and the brightest areas found at higher latitudes and on the trailing hemisphere, where temperatures remain low. As you rest and breathe slowly, consider the patience required for such a process to unfold. The thermal segregation of Iapetus has been occurring for hundreds of millions of years, perhaps billions. Each day, a tiny amount of ice sublimates from the dark regions and refreezes on the bright regions. Each year, the contrast between the two hemispheres grows slightly more pronounced. Each million years, the dichotomy becomes more firmly established. This is geology on a timescale that dwarfs human comprehension, a slow and silent transformation occurring in the cold darkness of the outer solar system, far from any watching eyes. The great dichotomy of Iapetus teaches us something profound about the interconnectedness of cosmic processes. A small dark moon named Phoebe, captured from the Kuiper belt billions of years ago, sheds particles into space through micrometeorite bombardment. These particles form a vast invisible ring around Saturn. Iapetus, orbiting closer to Saturn, sweeps through this ring and accumulates the dark material on its leading hemisphere. The dark material absorbs sunlight and warms the surface, driving the sublimation and migration of ice. Over eons, these processes combine to create one of the most visually striking worlds in the solar system. This is the beauty of planetary science, the way that seemingly unrelated phenomena connect and influence one another across vast distances and timescales. The dichotomy of Iapetus is not the result of any single event or process, but rather the cumulative outcome of countless interactions between moons, particles, sunlight, and ice. Understanding this dichotomy requires us to think holistically, to see the solar system not as a collection of isolated objects, but as an interconnected system where everything influences everything else. Let the image of the two-faced moon settle into your mind as you continue to relax. Picture the dark hemisphere absorbing the feeble sunlight of the outer solar system, slowly warming under its carbon-rich blanket. Picture the bright hemisphere, gleaming white against the blackness of space, cold and pristine and ancient. Picture the boundary between them, where darkness and light meet in a complex dance of sublimation and deposition. This is Iapetus, the yin-yang moon, a world of contrasts and mysteries that has fascinated observers for more than 300 years. Chapter 3. The Equatorial Ridge, a mountain range like no other. As remarkable as the dichotomy of Iapetus may be, it is not the only feature that sets this moon apart from all others in the solar system. There is another characteristic of Iapetus, so strange, so unexpected, that when scientists first saw clear images of it, many initially refused to believe what they were seeing. This is the Equatorial Ridge, a chain of mountains that runs almost perfectly along the equator of Iapetus, giving the moon the appearance of a walnut or a world with a belt cinched tightly around its middle. The Equatorial Ridge was first glimpsed in images from the Voyager 2 spacecraft in 1981, but those images were too distant and too low in resolution to reveal its true nature. It was not until the Cassini spacecraft arrived at Saturn in 2004 and began its detailed survey of the Saturnian system that the ridge was seen clearly for the first time. The images that Cassini sent back were astonishing. Here was a mountain range that stretched for more than 800 miles along the equator, with peaks rising as high as 12 miles above the surrounding terrain. To put this in perspective, Mount Everest, the tallest mountain on Earth, rises only about 5.5 miles above sea level. The peaks of the Iapetan Ridge are more than twice as tall. The ridge is not continuous, but rather consists of a series of isolated peaks, elongated mountains, and sections of more continuous elevated terrain. In some places, the ridge forms a single sharp crest, while in others, it splits into parallel ranges separated by valleys. The width of the ridge varies from about 12 miles in narrow sections to more than 40 miles, where it spreads out into broader elevated regions. Everywhere, the ridge follows the equator with remarkable precision, deviating by no more than a degree or two from the exact midline of the moon. The existence of such a feature raises profound questions about the geological history of Iapetus. How could a mountain range form so precisely along the equator? What forces could have pushed up such enormous peaks on a small icy moon in the outer solar system? Why is there nothing similar on any other moon we have observed? Scientists have proposed several theories to explain the equatorial ridge, each with its own strengths and weaknesses. One of the earliest and most dramatic proposals suggests that the ridge is the remnant of a ring system that once orbited Iapetus itself. According to this theory, early in its history, Iapetus possessed a ring of debris, perhaps formed by the destruction of a small satellite or the capture of passing material. Over time, the particles in this ring gradually spiraled inward and fell onto the equator of Iapetus, piling up to form the ridge we see today. This ring collapse theory has a certain elegance to it. It naturally explains why the ridge follows the equator so precisely, since ring particles would have orbited in the equatorial plane and would have landed along the equator as they fell. It also explains the enormous height of the ridge, since a substantial ring could have deposited a tremendous amount of material over millions of years. However, the theory also faces challenges. The mechanics of ring collapse are complex, and it is not clear that material falling from a ring would pile up into a narrow ridge, rather than spreading out across a broader area. Another theory proposes that the ridge formed through tectonic processes driven by the death spinning of Iapetus. As we discussed earlier, Iapetus appears to have once rotated much faster than it does today, perhaps completing one rotation every 16 hours or so. This rapid rotation would have caused the moon to bulge outward at the equator, stretching the surface in the east-west direction. As tidal forces from Saturn gradually slowed the rotation, the equatorial bulge would have tried to shrink, compressing the surface in the east-west direction. This compression could have caused the crust to buckle and fold, pushing up a ridge along the equator. The death spinning theory is attractive because it connects the ridge to another unusual feature of Iapetus, its oblate shape. Both features can be explained as consequences of the same process, the transition from rapid rotation to slow rotation early in the Moon's history. However, the theory also faces challenges. The amount of compression required to push up 12-mile-high mountains is enormous, and it is not clear that the icy crust of Iapetus could have accommodated such deformation without fracturing in other ways that we do not observe. A third theory suggests that the ridge formed through convective processes in the interior of Iapetus. According to this idea, heat from the decay of radioactive elements in the Moon's rocky core drove convection currents in the overlying ice mantle. These currents could have created a pattern of upwelling along the equator, pushing up the crust and forming the ridge. This theory is similar to the processes that create mid-ocean ridges on Earth, where convection in the mantle drives the spreading of tectonic plates. The convective theory has the advantage of invoking well-understood physical processes, but it too faces challenges. Iapetus is a small body with a relatively thin ice mantle, and it is not clear that convection could have been vigorous enough to create such a dramatic feature. Additionally, convective ridges on Earth are associated with volcanic activity and the creation of new crust, features that are not observed on Iapetus. A fourth possibility is that the ridge formed through a combination of processes. Perhaps an initial ridge was created by one mechanism, such as ring collapse or despinning, and was then modified and enhanced by other processes over billions of years. The complex structure of the ridge with its varying width, multiple crests, and sections of different character may reflect this composite origin. Whatever its origin, the equatorial ridge has had a profound influence on the subsequent geological history of Iapetus. The ridge acts as a barrier to the migration of surface materials, influencing the distribution of the dark coating and the patterns of crater formation. Impact craters on and near the ridge show complex patterns of degradation and infilling, suggesting that the ridge has been modified by impacts over billions of years. Some sections of the ridge have been partially buried by dark material from Cassini Regio, while others remain bright and prominent. The peaks of the equatorial ridge are among the most dramatic landscapes in the solar system. Imagine standing at the base of one of these mountains, looking up at a wall of ice and rock that rises 12 miles into the black sky. The slope before you stretches upward at angles that would be challenging to climb even in the low gravity of Iapetus. Far above, the peak catches the dim light of the distant sun, gleaming against the stars. Behind you, the surface of Iapetus stretches away to the curved horizon. Dark on one side, bright on the other, a world of contrasts and wonders. The ridge is most prominent within Cassini Regio, the dark leading hemisphere, where it stands out as a bright feature against the surrounding darkness. Here, the peaks of the ridge have remained relatively free of dark material, either because the steep slopes prevent accumulation or because the ridge was already in place when the dark coating began to form. The contrast between the bright ridge and the dark plains creates some of the most visually striking landscapes on Iapetus, a world that is already remarkable for its visual contrasts. On the trailing hemisphere, within Roncevaux Terra, the ridge is less prominent and in some places seems to disappear entirely. This may reflect differences in the original formation of the ridge, or it may be the result of subsequent geological processes that have modified or buried sections of the ridge over billions of years. The relationship between the ridge and the dichotomy is complex and not fully understood, one of many questions about Iapetus that await future exploration. As you continue to rest and relax, let the image of the equatorial ridge form in your mind. Picture a wall of ice and rock stretching from horizon to horizon, following the exact midline of this distant world. Picture peaks rising higher than any mountain on Earth, their summits lost in the blackness of space. Picture the ancient silence of this place, undisturbed for billions of years, waiting patiently for the day when human explorers might stand upon its slopes and gaze out at the ringed wonder of Saturn hanging in the sky. The equatorial ridge of Iapetus is a reminder that the universe is full of surprises, full of features and phenomena that we could never have predicted from first principles. When scientists first began to study the moons of the outer planets, no one imagined that they would find a world with a mountain range running precisely along its equator. No one predicted the 12-mile peaks, the complex structure, the mysterious origin. Iapetus has taught us humility, reminding us that nature is always more creative and more surprising than our theories anticipate. Chapter 4. Physical Dimensions and the Architecture of a Frozen World. Having explored the most visually striking features of Iapetus, let us now turn our attention to the fundamental physical properties that define this moon. Understanding the size, mass, density, and composition of Iapetus helps us place it in context within the larger family of Saturn's satellites and provides clues about its formation and evolution over billions of years. Iapetus ranks as the third largest moon of Saturn, smaller than the giant Titan and the substantial Rhea, but larger than all of Saturn's other natural satellites. Its mean diameter measures approximately 914 miles, a figure that places it in the same size class as some of the larger asteroids and dwarf planets. If you were to set Iapetus down next to the dwarf planet Ceres, the largest object in the asteroid belt, you would find them to be nearly identical in size, cosmic twins separated by hundreds of millions of miles of empty space. To visualize the scale of Iapetus, imagine a sphere slightly smaller than the distance from Los Angeles to Denver. You could fit approximately 3.5 Iapetuses side by side across the diameter of Earth's moon, or nearly 400 Iapetuses within the volume of our own planet. This is a substantial world by the standards of planetary satellites, large enough to have achieved hydrostatic equilibrium, the state in which gravity has pulled the body into a roughly spherical shape. The mass of Iapetus has been determined with great precision through careful tracking of the Cassini spacecraft as it flew past the moon. Each time Cassini approached Iapetus, the moon's gravity tugged on the spacecraft, altering its trajectory by a small but measurable amount. By analysing these gravitational perturbations, scientists calculated that Iapetus has a mass of approximately 1.806 times 10 to the 21st kilograms. In more familiar terms, this is about 1.8 million trillion metric tons, or roughly 2% of the mass of Earth's moon. The combination of Iapetus's size and mass allows us to calculate its density, a crucial property that reveals information about the moon's internal composition. Dividing the mass by the volume yields a density of approximately 1.08 grams per cubic centimetre. This is a remarkably low value, only slightly denser than liquid water and far less dense than rock. For comparison, Earth has a density of about 5.5 grams per cubic centimetre, and even our moon, which lacks a large iron core, has a density of 3.3 grams per cubic centimetre. The low density of Iapetus tells us that this moon is composed primarily of water ice, with only a modest fraction of denser rocky material. Scientists estimate that Iapetus is roughly 75 to 80% ice by mass, with the remaining 20 to 25% consisting of silicate rocks and possibly some organic compounds. This composition is typical of the mid-sized moons of the outer solar system, which formed in regions of the solar nebula where temperatures were cold enough for water to condense into solid ice. The internal structure of Iapetus is believed to be relatively simple, consisting of a small rocky core surrounded by a thick mantle of water ice. The rocky core probably measures between 200 and 300 miles in diameter, depending on the exact proportions of rock and ice. This core would be composed primarily of silicate minerals, perhaps with some iron and other metals, similar to the rocky material found in asteroids and the inner planets. Surrounding the core, the ice mantle extends all the way to the surface, a frozen ocean hundreds of miles deep. Unlike some of Saturn's other moons, such as Enceladus with its subsurface ocean and active geysers, Iapetus shows no evidence of liquid water beneath its surface. The moon appears to be frozen solid throughout, a consequence of its small size and its great distance from Saturn, which minimizes the tidal heating that keeps some other moons geologically active. The surface gravity on Iapetus is quite weak, only about 0.022 times the surface gravity of Earth. If you weigh 150 pounds on Earth, you would weigh only about 3.3 pounds on Iapetus. This feeble gravity has important implications for the behavior of surface materials and the morphology of geological features. Impact craters on Iapetus tend to be shallower and more degraded than similar-sized craters on bodies with stronger gravity, because the weak gravity allows crater walls to slump and collapse more easily over time. The escape velocity from Iapetus, the speed required to break free of the moon's gravitational pull entirely, is only about 0.58 kilometers per second, or roughly 1,300 miles per hour. This is slow enough that a sufficiently powerful explosion could blast material completely off the surface and into orbit around Saturn. Indeed, some scientists have speculated that impacts on Iapetus may have contributed material to Saturn's ring system, though the evidence for this remains inconclusive. One of the most intriguing aspects of Iapetus's shape is its pronounced oblateness, the degree to which it bulges at the equator and flattens at the poles. Careful measurements from the Cassini spacecraft revealed that the equatorial diameter of Iapetus is about 29 miles greater than its polar diameter, giving the moon a noticeably squashed appearance. This degree of oblateness is far greater than would be expected for a body rotating as slowly as Iapetus does today. The explanation for this anomalous shape lies in the moon's distant past. Early in its history, Iapetus rotated much faster than it does now, perhaps completing one rotation every 16 hours or so. This rapid rotation generated strong centrifugal forces that push material outward at the equator, creating a pronounced equatorial bulge. At this time, the interior of Iapetus was still warm enough to be somewhat plastic, allowing it to deform in response to the rotational forces. As Iapetus cooled and its interior froze solid, this oblate shape became locked in, preserved like a fossil of the moon's earlier, more dynamic state. Meanwhile, tidal forces from Saturn gradually slowed the moon's rotation, eventually bringing it to its current period of 79.3 Earth days. But by the time this spinning occurred, the interior was already frozen solid, unable to relax back to a more spherical shape. The result is a moon that looks like it should be rotating much faster than it actually is, a frozen relic of a bygone era. The surface temperature on Iapetus varies dramatically depending on location, time of day, and the local albedo of the surface. The dark regions of Cassini Regio absorb most of the incoming sunlight and can warm to temperatures as high as -208 degrees Fahrenheit during the long Iapetan day. The bright regions of Roncevaux Terra reflect most of the sunlight away and remain much colder, with temperatures dropping as low as -290 degrees Fahrenheit in shadow. These temperature differences, as we discussed earlier, drive the thermal segregation process that maintains and enhances the dichotomy between the two hemispheres. The dark regions are warm enough to cause significant sublimation of water ice, while the bright regions are cold enough to trap the migrating water vapour and add it to the ice deposits. This ongoing process continues to shape the surface of Iapetus even today, though on timescales far too slow for human observation. The day-night cycle on Iapetus is extraordinarily long by terrestrial standards. Because the Moon is tidally locked to Saturn, its rotation period equals its orbital period of 79.3 Earth days. This means that a single day on Iapetus from sunrise to sunrise lasts nearly 80 Earth days. During this time, the surface experiences roughly 40 days of continuous sunlight, followed by 40 days of continuous darkness, with only brief periods of twilight at dawn and dusk. This long day-night cycle has important implications for the thermal behaviour of the surface. During the extended day, the surface has time to warm significantly, reaching temperatures that would not be possible with a shorter day. During the extended night, the surface cools dramatically, losing heat to space over weeks of continuous darkness. These extreme temperature swings stress the surface materials, potentially contributing to the breakdown of rocks and the modification of geological features over time. As you rest and breathe slowly, consider the vast spans of time over which Iapetus has existed. This moon formed approximately 4.5 billion years ago, during the same epoch that saw the birth of the Sun, the planets, and all the other bodies of our solar system. For most of that time, Iapetus has orbited Saturn in silence and darkness, its surface slowly evolving under the influence of impacts, radiation, and the gentle processes of sublimation and deposition. The features we observe today are the cumulative result of billions of years of patient geological work, a record written in ice and rock that scientists are only beginning to read. Chapter 5. The Orbital Dance, Iapetus and the Saturnian System. Every world in our solar system moves through space in its own unique way, tracing an orbital path that reflects the gravitational influences of the Sun, the planets, and countless smaller bodies. The orbit of Iapetus is particularly interesting, distinguished by several unusual characteristics that set it apart from Saturn's other major moons and provide clues about its origin and evolution. Iapetus orbits Saturn at an average distance of approximately 2.21 million miles, making it by far the most distant of Saturn's major satellites. To put this distance in perspective, our own moon orbits Earth at an average distance of only about 239,000 miles, less than 1/9 the distance between Iapetus and Saturn. If you were standing on the surface of Iapetus and looking towards Saturn, the ringed planet would appear about the same size as a tennis ball held at arm's length, beautiful and majestic, but noticeably smaller than the view enjoyed by observers on Saturn's inner moons. The orbital period of Iapetus, the time required to complete one circuit around Saturn, is approximately 79.3 Earth days. This is by far the longest orbital period of any of Saturn's major moons, a consequence of the great distance between Iapetus and its parent planet. Kepler's laws of planetary motion tell us that the farther a body is from the object it orbits, the longer its orbital period will be, and Iapetus follows this rule precisely. One of the most distinctive features of Iapetus's orbit is its significant inclination relative to Saturn's equatorial plane. While most of Saturn's major moons orbit within a few degrees of the equatorial plane, Iapetus orbits at an inclination of approximately 15.5 degrees. This tilted orbit means that Iapetus spends much of its time above or below the plane of Saturn's rings, offering views of the ring system that are impossible from the more equatorially orbiting moons. The inclined orbit of Iapetus has important implications for its interaction with the Phoebe ring, the vast cloud of dark material that we discussed earlier. Because the Phoebe ring is also inclined to Saturn's equatorial plane, at an angle of about 27 degrees, Iapetus passes through the ring twice during each orbit, once on the way up and once on the way down. These passages allow the moon to sweep up dark material from the ring, contributing to the formation of the dichotomy that makes Iapetus so visually distinctive. The eccentricity of Iapetus's orbit, a measure of how much it deviates from a perfect circle, is approximately 0.028. This is a relatively small eccentricity, meaning that the orbit is nearly circular, but it is larger than the eccentricities of most of Saturn's other major moons. At its closest approach to Saturn, called periapsis, Iapetus comes within about 2.13 million miles of the planet. At its farthest point, called apoapsis, the distance increases to about 2.29 million miles. This variation of about 160,000 miles over the course of each orbit causes slight changes in the apparent size of Saturn as seen from Iapetus. The tidal locking of Iapetus, which we have mentioned several times, is a crucial aspect of its orbital dynamics. Like our own moon, Iapetus always keeps the same face pointed towards Saturn, a consequence of gravitational interactions that have synchronized the moon's rotation with its orbital motion. This synchronization means that the same hemisphere of Iapetus always leads as the moon moves along its orbit, while the opposite hemisphere always trails behind. This is why the dark material from the Phoebe ring accumulates preferentially on the leading hemisphere, creating the distinctive pattern of the dichotomy. The process of tidal locking occurs over millions of years through the action of tidal forces. When a moon is not tidally locked, the gravitational pull of its parent planet creates a slight bulge on the near side of the moon. If the moon is rotating faster than it is orbiting, this bulge is carried slightly ahead of the line connecting the moon to the planet. The gravitational pull on this bulge creates a torque that gradually slows the moon's rotation until it matches the orbital period. Once this synchronization is achieved, the bulge remains aligned with the planet, and no further torque is applied. For Iapetus, the process of tidal locking would have occurred relatively slowly due to the moon's great distance from Saturn. Tidal forces decrease rapidly with distance, following an inverse cube law, so the tidal forces acting on Iapetus are much weaker than those acting on Saturn's inner moons. Scientists estimate that it may have taken several 100 million years for Iapetus to become tidally locked, during which time the moon's rotation gradually slowed from its initial rapid rate to its current leisurely pace of one rotation every 79 days. The great distance of Iapetus from Saturn also means that tidal heating, the internal heat generated by the flexing of a moon's interior due to tidal forces, is negligible. This is in stark contrast to some of Saturn's inner moons, particularly Enceladus, where tidal heating drives active geological processes, including cryovolcanism and the maintenance of a subsurface ocean. Iapetus, with its weak tidal forces and frozen interior, is geologically dead, a world where the only ongoing changes are the slow processes of impact cratering and thermal segregation. The orbital plane of Iapetus precesses over time, meaning that the orientation of the orbit slowly changes due to gravitational perturbations from Saturn's oblateness, the Sun, and other moons. This precession has a period of approximately 3,000 years, during which the orbit completes one full cycle of orientation changes. The precession affects the timing and geometry of Iapetus's passages through the Phoebe ring, potentially influencing the rate at which dark material accumulates on the leading hemisphere. From the perspective of an observer on Iapetus, the orbital motion creates a fascinating celestial display. Saturn hangs perpetually in the same part of the sky, never rising or setting, though it does appear to wobble slightly due to libration effects. The rings of Saturn are visible edge-on or at various angles depending on the position of Iapetus in its inclined orbit, sometimes appearing as a thin line across the planet's equator, and other times opening up to reveal their full glory. The sun rises and sets once every 79 days, tracing a path across the sky that varies with the seasons as Saturn orbits the sun. The other moons of Saturn would be visible from Iapetus as points of light moving against the background of stars. Titan, the largest of Saturn's moons, would be the most prominent, appearing as a bright orange-tinted star that completes one circuit around Saturn every 16 days. The smaller moons would be fainter and faster moving, some completing their orbits in just a day or two. Watching these moons from the surface of Iapetus would provide a constant reminder of the complex gravitational dance that governs the Saturnian system. The position of Iapetus in the Saturnian system has led some scientists to question whether it formed in its current location or migrated there from elsewhere. Most of Saturn's major moons orbit in a regular pattern, with distances from Saturn that follow predictable relationships. Iapetus, with its distant inclined orbit, does not fit this pattern, as well as the other moons. Some researchers have proposed that Iapetus formed closer to Saturn and was later scattered outward by gravitational interactions with other moons or passing objects. Others suggest that Iapetus formed in place but from a different source of material than the inner moons. The question of Iapetus's origin remains open, one of many mysteries about this moon that await future investigation. What we do know is that Iapetus has occupied its current orbit for billions of years, long enough for the slow processes of impact cratering and thermal segregation to shape its surface into the remarkable landscape we observe today. The orbital characteristics of this moon, its great distance from Saturn, its inclined path through space, its synchronous rotation, all contribute to making Iapetus one of the most distinctive and fascinating objects in the outer solar system. As you continue to rest and relax, imagine the slow, stately motion of Iapetus around Saturn. Picture this frozen world tracing its elliptical path through the darkness, rising above and below the plane of the rings, sweeping through the invisible cloud of the Phoebe ring, always keeping the same face turned toward its giant parent planet. This orbital dance has continued for longer than life has existed on Earth, and it will continue for billions of years into the future, a cosmic rhythm as reliable as the beating of a heart. Given that Iapetus is Saturn's third largest moon, that it appears to have a similar composition to Saturn's other prominent moons, and that it has almost no orbital eccentricity, even the cleverest of gravitational encounters struggle to explain how Iapetus might have migrated out of Saturn's equatorial plane, if that is indeed where it originally formed. The significant inclination of approximately 15.5 degrees raises profound questions about the early history of the Saturnian system and the processes that shaped the orbits of its moons. These questions connect Iapetus to the broader story of planetary formation and evolution, reminding us that every world in our solar system carries within it a record of the events that shaped it. Chapter 6, The Ancient Surface Craters and the Record of Cosmic Violence. The surface of Iapetus is a chronicle written in ice and stone, a record of billions of years of cosmic history preserved in the craters, basins, and scarred terrain that cover this ancient moon. Unlike worlds with active geology that constantly resurface themselves, erasing the evidence of past events, Iapetus has remained largely unchanged for eons, its surface a museum of impacts stretching back to the earliest days of the solar system. When we look at Iapetus through the eyes of spacecraft cameras, we see a world pockmarked with craters of every size, from tiny pits just a few feet across to enormous basins hundreds of miles in diameter. These craters are the fingerprints of countless collisions, each one marking the moment when a piece of cosmic debris, an asteroid, a comet, or a fragment of some destroyed world struck the surface of Iapetus and left its mark forever. The largest impact basin on Iapetus is named Turgis, a vast depression approximately 360 miles in diameter that dominates a significant portion of the moon's surface. To appreciate the scale of Turgis, imagine a crater so large that it could swallow the entire state of Montana with room to spare. The walls of this basin rise miles above its floor, creating a ring of mountains that would dwarf any terrestrial range. The floor of Turgis is itself cratered, bearing the scars of smaller impacts that occurred after the basin-forming event, a record within a record of the ongoing bombardment that has shaped this world. The impact that created Turgis must have been a cataclysmic event, releasing energy equivalent to billions of nuclear weapons and sending shockwaves rippling through the icy crust of Iapetus. The impactor itself was probably several tens of miles in diameter, a mountain of rock and ice travelling at tremendous speed. When it struck, it excavated millions of cubic miles of material, some of which fell back to form the basin floor, while the rest was scattered across the surrounding terrain, or even ejected into space. Other major impact basins on Iapetus include Engelia, Gerin, and Falseron, each over 200 miles across. These basins, along with Turgis, represent the largest impacts that Iapetus has experienced since its formation, events that would have been visible from Earth if any eyes had been watching 4 billion years ago. The distribution of these large basins across the surface of Iapetus provides clues about the history of bombardment in the outer solar system, helping scientists understand the population of impactors and the rates at which collisions occurred at different times in solar system history. Between the large basins, the surface of Iapetus is covered with countless smaller craters, creating a landscape that resembles the cratered highlands of our own moon. These smaller craters range from fresh, sharp-rimmed features that formed relatively recently to ancient, degraded structures that have been softened and partially filled by billions of years of subsequent impacts and surface processes. The density of craters on the oldest surfaces of Iapetus is among the highest in the solar system, indicating that this moon has been accumulating impacts since the very earliest era of solar system history. The morphology of craters on Iapetus reflects the unique properties of this icy world. Because the surface is composed primarily of water ice rather than rock, craters on Iapetus behave somewhat differently than craters on rocky bodies like the Moon or Mercury. Ice is weaker than rock and flows more easily over geological timescales, causing crater walls to slump and crater floors to rise as the ice slowly relaxes toward a more stable configuration. This process, called viscous relaxation, tends to make older craters shallower and more subdued than younger craters of the same size. The weak gravity of Iapetus also influences crater morphology. With surface gravity only about 2% of Earth's, the walls of craters on Iapetus can support steeper slopes than would be possible on a more massive world. However, The weak gravity also means that ejecta, the material blasted out of a crater during an impact, travels farther before falling back to the surface. This creates extensive ejecta blankets around fresh craters, aprons of debris that can extend for many crater diameters from the rim. One of the most interesting aspects of crater morphology on Iapetus is the relationship between craters and the dichotomy. Within Cassini Regio, the dark leading hemisphere, many craters have bright floors where the impact has excavated through the dark surface coating to expose the underlying ice. These bright floored craters provide direct evidence that the dark material is a relatively thin surface layer rather than a fundamental property of the Moon's composition. The thickness of the dark layer can be estimated from the depth of craters that do and do not penetrate through it, suggesting that the coating is typically only a few feet to a few tens of feet thick in most areas. Conversely, some craters in Roncevaux Terra, the bright trailing hemisphere, have dark floors or dark patches on their walls. These features may represent places where dark material has accumulated in topographic lows, or where impacts have exposed older, darker layers beneath the fresh ice surface. The complex interplay between craters and surface coloration adds another layer of information to the geological history recorded on the surface of Iapetus. The ages of different surfaces on Iapetus can be estimated by counting craters and comparing the crater densities to models of the impact rate over time. Surfaces with more craters are generally older, having had more time to accumulate impacts, while surfaces with fewer craters are younger. Using this technique, scientists have determined that most of the surface of Iapetus is extremely ancient, dating back to the period of heavy bombardment that occurred in the first billion years of solar system history. There are no large areas of young, sparsely cratered terrain on Iapetus, indicating that the Moon has been geologically dead for billions of years. The craters of Iapetus have been given names drawn from the medieval French epic, the Song of Roland, continuing the naming theme established for features on this moon. Names like Charlemagne, Roland, Turpin, and Balagant grace the rims and floors of impact structures, connecting this distant frozen world to the rich tradition of human storytelling. These names remind us that the exploration of space is not just a scientific endeavour, but also a cultural one, a way of extending human presence and meaning into the cosmos. As you rest and breathe slowly, imagine the surface of Iapetus stretching away beneath you, a landscape of craters and ridges and ancient ice. Picture the walls of Turgis rising in the distance, a ring of mountains marking the site of an ancient cataclysm. Picture the smaller craters scattered across the terrain, each one a record of a moment of violence frozen in time. This is a world where nothing has been erased, where every event leaves its mark forever, a chronicle of cosmic history written in the language of impacts. The craters of Iapetus connect this moon to the broader story of the solar system, a story of formation and bombardment, of worlds being built up and torn apart by collisions over billions of years. Every crater on Iapetus has a counterpart somewhere else in the solar system, a sibling impact that occurred when the same population of debris struck other worlds. By studying the craters on Iapetus and comparing them to craters on other moons and planets, scientists can piece together the history of bombardment throughout the solar system, understanding how the rate and intensity of impacts has changed over time. The ancient surface of Iapetus is a gift to science, a preserved record of events that have been erased on more geologically active worlds. On Earth, plate tectonics and erosion constantly renew the surface, destroying the evidence of ancient impacts. On Io, volcanic activity buries craters under fresh lava flows. On Enceladus, Cryovolcanism and tectonic activity resurface portions of the Moon. But on Iapetus, the geological clock stopped billions of years ago, leaving behind a surface that has changed only through the slow accumulation of new impacts and the patient work of thermal segregation. Chapter 7. Cassini Regio, the Dark Hemisphere Revealed. Let us now journey to the dark side of Iapetus, to the vast province known as Cassini Regio that covers most of the leading hemisphere of this two-faced moon. This is a landscape unlike any other in the solar system, a world of deep browns and blacks, where the feeble sunlight of the outer solar system is almost entirely absorbed by the carbon-rich materials that coat the surface. Cassini Regio takes its name from Giovanni Domenico Cassini, the astronomer who discovered Iapetus in 1671 and first proposed that the moon's strange brightness variations were caused by one hemisphere being darker than the other. It is fitting that this dark province bears his name, honouring the scientist who first glimpsed the mystery that would puzzle astronomers for more than 3 centuries. The dark material that covers Cassini Regio is among the darkest substances found anywhere in the solar system. With an albedo of only about 0.04, meaning it reflects only 4% of incoming sunlight, this material is darker than charcoal, darker than fresh asphalt, approaching the blackness of soot or carbon black. If you were standing on the surface of Cassini Regio, you would find yourself in a landscape of profound darkness, where even the brightest noon would seem like deep twilight by terrestrial standards. The composition of the dark material has been studied extensively using spectroscopic observations from both Earth-based telescopes and the Cassini spacecraft. These observations reveal that the dark coating contains a complex mixture of organic compounds, carbon-rich molecules that absorb light across a wide range of wavelengths. The exact composition remains uncertain, but the material appears to include polycyclic aromatic hydrocarbons, complex molecules built from rings of carbon atoms that are common in the interstellar medium and in primitive solar system bodies. In addition to organic compounds, the dark material contains iron-bearing minerals that contribute to its reddish-brown coloration. These minerals may include iron oxides, iron sulfides, or iron-bearing silicates mixed with the organic compounds to create the distinctive spectral signature observed from Cassini Regio. The presence of iron suggests that the dark material is not purely organic but includes a component of rocky or metallite material consistent with an origin from the outer solar system, where such materials are common. The dark material appears to lie on top of other geologic features seen on Iapetus, implying that the event which formed the dark coating occurred later in the Moon's history. This stratigraphic relationship is visible in the bright floored craters that dot Cassini Regio, where impacts have punched through the dark layer to reveal the ice beneath. The dark coating is clearly a surface phenomenon, a veneer applied to an already formed and cratered landscape rather than a fundamental property of the Moon's composition. The thickness of the dark coating varies across Cassini Regio, from areas where it is only a few inches thick to regions where it may extend several feet or even tens of feet below the surface. The thickest deposits are found near the centre of the leading hemisphere, where the accumulation of material from the Phoebe ring has been most intense. Toward the edges of Cassini Regio, the coating thins and becomes patchy, eventually giving way to the bright ice of Roncevaux Terra. The boundary between Cassini Regio and Roncevaux Terra is not a sharp line, but a gradual transition zone where dark and bright materials intermingle. In this transition zone, the surface displays a complex pattern of dark and bright patches, with fingers of darkness extending into the bright terrain and islands of brightness persisting within the dark region. This pattern reflects the ongoing processes of thermal segregation that continue to shape the dichotomy, with ice sublimating from warmer, darker areas and refreezing in colder, brighter areas. Within Cassini Regio, the equatorial ridge stands out as a relatively bright feature against the surrounding darkness. The peaks of the ridge have remained largely free of dark material, either because the steep slopes prevent accumulation or because the ridge was already in place when the dark coating began to form. This contrast between the bright ridge and the dark plains creates some of the most visually striking landscapes on Iapetus, a world that is already remarkable for its visual contrasts. The temperature within Cassini Regio is significantly higher than in the bright regions of Iapetus, a consequence of the dark material's ability to absorb sunlight. During the long Iapetan day, the surface of Cassini Regio can warm to temperatures as high as -208 degrees Fahrenheit, about 50 degrees warmer than the bright regions. This temperature difference drives the thermal segregation process, causing ice to sublimate from the dark regions and migrate to the colder, brighter regions. The warmth of Cassini Regio has important implications for the stability of water ice on the surface. At the temperatures reached during the Iapetan day, water ice sublimates at a measurable rate, slowly transforming from solid to gas and escaping into the thin exosphere that surrounds the Moon. Over millions of years, this sublimation has removed most of the ice that once covered the leading hemisphere, leaving behind the concentrated dark residue that we observe today. The landscape of Cassini Regio is dominated by impact craters, just like the rest of Iapetus, but the dark coating gives these craters a distinctive appearance. Fresh craters with bright floors stand out sharply against the dark background, their icy interiors gleaming like jewels set in black velvet. Older craters, whose floors have been covered by dark material over time, blend into the surrounding terrain, visible only as subtle variations in topography. Some of the most interesting features in Cassini Regio are the bright crater rays, streaks of bright material that radiate outward from fresh impact craters. These rays are composed of ice excavated from beneath the dark coating and scattered across the surface by the force of the impact. Over time, the rays darken as they accumulate dark material from the ongoing rain of Phoebe ring particles, eventually blending into the surrounding terrain. The presence of bright rays around some craters and their absence around others provides information about the relative ages of different impacts. As you rest and let your mind wander across this dark landscape, imagine the silence and stillness of Cassini Regio. No wind stirs the surface, no water flows, no life moves across the ancient terrain. The only changes that occur here happen on timescales of millions of years. The slow accumulation of dark particles from space, the patient sublimation of ice, the occasional violence of an impact. This is a world frozen in time, a snapshot of conditions that have persisted for longer than complex life has existed on Earth. The darkness of Cassini Regio is not absolute. Even here, in one of the darkest places in the solar system, there is light. The distant sun, appearing as a bright star rather than the blazing disk we know from Earth, provides enough illumination to see by, if only barely. Saturn, hanging perpetually in the sky, reflects sunlight onto the surface, adding a soft glow to the darkness. And the stars, undimmed by any atmosphere, blaze with a brilliance that would take your breath away, a canopy of light surrounding this world of shadow. The dark hemisphere of Iapetus is a reminder that darkness and light are relative concepts, that what seems utterly black from one perspective may contain subtle gradations and variations when examined more closely. The scientists who study Cassini Regio have learned to see in shades of darkness, distinguishing between the deep black of the darkest regions and the slightly lighter tones of areas where bright material mixes with dark. This attention to subtle differences has revealed much about the processes that have shaped this hemisphere and continue to shape it today. Chapter 8. Roncevaux Terra, the bright hemisphere and its icy splendour. From the darkness of Cassini Regio, let us now travel to the opposite side of Iapetus, to the gleaming white expanse of Roncevaux Terra. This is the trailing hemisphere of the moon, the side that faces backward as Iapetus moves along its orbit, and it presents a stark contrast to the dark leading hemisphere we have just explored. Roncevaux Terra takes its name from the Battle of Roncevaux Pass, a famous engagement from the Song of Roland in which the rearguard of Charlemagne's army was ambushed and destroyed. The name connects this bright, icy landscape to the same medieval epic that provides names for craters and other features across Iapetus, weaving a thread of human storytelling through the alien terrain of this distant moon. The surface of Roncevaux Terra is composed primarily of water ice, the same substance that makes up glaciers and icebergs on Earth, but existing here in conditions far colder and more alien than anything found on our world. This ice reflects approximately 60% of the sunlight that falls upon it, giving Roncevaux Terra an albedo that rivals fresh snow. If you were standing on this hemisphere, the landscape around you would gleam with a brightness that would seem almost painful after the darkness of Cassini Regio. The ice of Roncevaux Terra is not pure white, but displays subtle variations in colour and brightness that reveal information about its composition and history. In some areas, the ice has a slightly bluish tint, indicating that it is relatively pure and free of contaminants. In other regions, the ice takes on a yellowish or brownish cast, suggesting the presence of small amounts of organic compounds or other impurities mixed with the frozen water. The brightness of Roncevaux Terra is maintained by the ongoing process of thermal segregation that we have discussed several times. Water vapour sublimating from the warmer, darker regions of Cassini Regio migrates across the surface of Iapetus and refreezes when it reaches the colder trailing hemisphere. This continuous deposition of fresh ice keeps Roncevaux Terra bright and prevents the accumulation of dark material that would otherwise darken the surface over time. The temperature in Roncevaux Terra is significantly colder than in Cassini Regio, a consequence of the bright ice reflecting most of the incoming sunlight rather than absorbing it. During the Iapetan day, the surface temperature in the brightest regions may reach only about -260 degrees Fahrenheit, more than 50 degrees colder than the dark regions. During the long Iapetan night, temperatures plunge even further, approaching -300 degrees Fahrenheit in the coldest areas. These extreme cold temperatures have important implications for the behaviour of surface materials. At such low temperatures, water ice becomes extremely hard and brittle, behaving more like rock than like the relatively soft ice we are familiar with on Earth. The ice of Roncevaux Terra has probably remained frozen solid for billions of years, preserving the record of ancient impacts and other geological events with remarkable fidelity. The landscape of Roncevaux Terra is dominated by impact craters, just like the rest of Iapetus, but here the craters appear in shades of white and grey, rather than the dark tones of Cassini Regio. Fresh craters are particularly bright, their walls and floors composed of ice that has been freshly exposed by the impact and has not yet had time to accumulate any dark material. Older craters are slightly darker, their surfaces having collected a thin patina of dark particles over millions of years. The equatorial ridge extends into Roncevaux Terra, though it is less prominent here than in Cassini Regio. In some areas, the ridge seems to disappear entirely, either because it was never as well developed on this hemisphere, or because subsequent geological processes have modified or buried it. The relationship between the ridge and the dichotomy remains one of the many puzzles of Iapetus, a question that future missions may help to answer. One of the most striking features of Roncevaux Terra is the way it interacts with the transition zone at the boundary with Cassini Regio. Here, bright ice and dark material meet in complex patterns, creating a landscape of stark contrasts where brilliant white patches sit adjacent to deep black regions. This transition zone is where the processes of thermal segregation are most active, with ice constantly sublimating from warmer areas and refreezing in colder areas, slowly but inexorably sharpening the boundary between the two hemispheres. The bright hemisphere of Iapetus offers a different kind of beauty than the dark hemisphere, a beauty of light and reflection rather than shadow and absorption. Standing on Roncevaux Terra, you would see the distant sun reflected in the icy surface around you, creating a landscape of sparkle and gleam. The stars would be harder to see against the bright surface, but Saturn would be visible, its rings catching the sunlight and glowing with a soft golden light. As you rest and relax, let the image of Roncevaux Terra fill your mind. Picture a landscape of ice stretching to the horizon, bright and clean and ancient. Picture the craters scattered across this frozen plain, their walls and floors gleaming in the dim sunlight. Picture the silence of this place, the absolute stillness of a world where nothing has changed for billions of years. This is a place of peace and tranquility, a frozen sanctuary in the outer reaches of the solar system. The contrast between Roncevaux Terra and Cassini Regio is one of the most remarkable features of Iapetus, a visual demonstration of the processes that have shaped this moon over billions of years. The two hemispheres are like two different worlds joined together, a world of darkness and a world of light, each with its own character and its own beauty. Together, they make Iapetus one of the most visually distinctive objects in the solar system, a moon that captures the imagination and invites us to wonder at the diversity of worlds that exist beyond our own. Chapter 9: Spacecraft Exploration and the Cassini Mission. The story of our exploration of Iapetus entered a new chapter with the dawn of the space age, when humanity gained the ability to send robotic emissaries to the distant worlds of the outer solar system. The spacecraft that have visited Iapetus have transformed our understanding of this moon, revealing details that could never have been seen from Earth, and raising new questions that continue to drive scientific investigation. The first spacecraft to encounter Iapetus were the twin Voyager probes, launched by NASA in 1977 to take advantage of a rare alignment of the outer planets. Voyager 1 flew past Saturn in November 1980, followed by Voyager 2 in August 1981. Both spacecraft captured images of Iapetus, though from considerable distances that limited the detail that could be resolved. The Voyager images confirmed the basic features of Iapetus that had been inferred from Earth-based observations, including the dramatic brightness dichotomy between the leading and trailing hemispheres. For the first time, scientists could see the shape of Cassini Regio and Roncevaux Terra, the distribution of craters across the surface, and hints of the equatorial ridge that would later prove to be one of the moon's most remarkable features. But the Voyager images also raised new questions, revealing complexities in the surface that demanded closer investigation. The spacecraft that would provide that closer investigation was Cassini, named in honour of the astronomer who discovered Iapetus more than 3 centuries earlier. Cassini was launched in October 1997 and arrived at Saturn in July 2004, beginning a mission that would last more than 13 years and revolutionise our understanding of the Saturnian system. Cassini made several close approaches to Iapetus during its mission, each one providing new data and new insights into this mysterious moon. The closest approach occurred on September 10th, 2007, when Cassini flew within about 1,600 kilometers of the surface, close enough to resolve features just a few tens of meters across. The images and data returned from this flyby were stunning, revealing the surface of Iapetus in unprecedented detail. The Cassini images showed the equatorial ridge in sharp relief for the first time, revealing its true nature as a chain of mountains running precisely along the equator. The height of the ridge, reaching up to 12 miles in some places, astonished scientists who had not expected to find such dramatic topography on a small icy moon. The images also revealed the complex structure of the ridge, with its multiple peaks, parallel ranges, and sections of varying character. The dichotomy between Cassini Regio and Roncevaux Terra was also revealed in new detail by the Cassini spacecraft. The images showed the gradual transition between the dark and bright regions, the bright floored craters within Cassini Regio, and the complex patterns of dark and bright material in the transition zone. Spectroscopic observations provided information about the composition of the surface materials, confirming the presence of water ice in the bright regions and carbon-rich organic compounds in the dark regions. The Cassini spacecraft provided detailed images and data about Iapetus, revealing its unique topography and surface characteristics. These observations have transformed our understanding of this moon, replacing speculation with solid scientific knowledge and opening new avenues of investigation that will keep scientists busy for decades to come. One of the most important contributions of the Cassini mission was the measurement of Iapetus's shape and gravity field. By tracking the spacecraft's trajectory as it flew past the moon, scientists were able to determine the mass and density of Iapetus with unprecedented precision. These measurements confirmed that Iapetus is composed primarily of water ice, with only a small fraction of denser rocky material. They also revealed the pronounced oblateness of the moon, the equatorial bulge that suggests a history of rapid rotation early in its existence. The Cassini mission also provided new information about the thermal properties of Iapetus's surface. Infrared observations showed that the dark regions are significantly warmer than the bright regions, exactly as predicted by the thermal segregation model. These temperature measurements provided crucial support for the theory that the dichotomy is maintained and enhanced by the sublimation and migration of water ice, driven by the different heat-absorbing properties of dark and bright materials. The discovery of the Phoebe ring in 2009, made using the Spitzer Space Telescope, added another piece to the puzzle of Iapetus. This vast, diffuse ring of dark material, originating from the distant moon Phoebe, provides a source for the dark coating on Iapetus's leading hemisphere. The discovery of the ring confirmed the long-suspected connection between Phoebe and the dichotomy of Iapetus, explaining how dark material could have been deposited on the leading hemisphere over billions of years. The Cassini mission ended in September 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere to prevent any possibility of contaminating the potentially habitable moons Enceladus or Titan. But the data collected by Cassini continues to be analysed, and new discoveries about Iapetus and the other moons of Saturn continue to emerge from this rich data set. As you rest and breathe slowly, consider the remarkable journey that brought these images and data to us. A spacecraft built by human hands, launched from a planet 93 million miles from the Sun, travelled for 7 years across nearly 1 billion miles of empty space to reach Saturn. There it spent more than 13 years exploring the ringed planet and its moons, sending back data that has transformed our understanding of this distant corner of the solar system. This is one of the great achievements of human civilization, a testament to our curiosity, our ingenuity, and our determination to understand the universe we inhabit. The exploration of Iapetus is far from complete. The Cassini mission answered many questions but raised many more, and there is still much we do not understand about this remarkable moon. Future missions to Saturn may provide new opportunities to study Iapetus, perhaps with dedicated orbiters or even landers that could examine the surface in detail. Until then, we must content ourselves with the data we have, continuing to analyse and interpret the observations that Cassini and Voyager have provided. Chapter 10. Scientific Theories and Ongoing Mysteries. Despite decades of observation and the wealth of data returned by spacecraft, Iapetus remains a world of mysteries. Many questions about this moon have been answered, but many more remain open, challenging scientists to develop new theories and devise new observations that might reveal the truth. Let us explore some of these ongoing mysteries and the theories that have been proposed to explain them. The origin of the equatorial ridge remains one of the most debated questions in planetary science. As we discussed earlier, several theories have been proposed to explain this remarkable feature, including the collapse of a ring system, tectonic compression during dust spinning, and convective upwelling from the interior. Each theory has its strengths and weaknesses, and none has yet achieved universal acceptance among scientists. The ring collapse theory proposes that Iapetus once possessed a ring of debris that gradually spiraled inward and fell onto the equator, piling up to form the ridge. This theory naturally explains why the ridge follows the equator so precisely, since ring particles would have orbited in the equatorial plane. However, the theory faces challenges in explaining how the material could have piled up into such a narrow high ridge rather than spreading out across a broader area. The dust spinning theory proposes that the ridge formed when Iapetus's rotation slowed from a rapid initial rate to its current slow pace. As the rotation slowed, the equatorial bulge would have tried to shrink, compressing the crust in the east-west direction and causing it to buckle upward along the equator. This theory connects the ridge to the moon's oblate shape, explaining both features as consequences of the same process. However, the theory requires the icy crust to have behaved in ways that are not fully understood, and it is not clear that the compression would have been sufficient to create such high mountains. A third possibility has been suggested by Paolo Cisi Freire of Arecibo Observatory, who proposes that the ridge and Cassini Regio were created when Iapetus grazed the outer edges of Saturn's rings in the distant past. However, Freire's theory requires Iapetus to have been later ejected to its current distant orbit around Saturn. This dramatic scenario would explain several features of Iapetus, but requires a complex series of gravitational interactions that may be difficult to achieve. There are three critical observations that any model for the formation of the ridge has to satisfy. They are why the feature is sitting on the equator, why only on the equator, and why only on Iapetus. Any successful theory must explain all three of these observations, a challenge that has so far proven difficult to meet. The origin of the dichotomy is better understood than the origin of the ridge, but questions remain. The basic mechanism, the deposition of dark material from the Phoebe ring followed by thermal segregation, is widely accepted. But the details of this process are still being worked out. How thick is the dark coating in different areas? How long did it take to form? How has it evolved over time? These questions require continued analysis of the Cassini data and perhaps new observations from future missions. The composition of the dark material is another area of ongoing investigation. Spectroscopic observations have revealed the presence of organic compounds and iron-bearing minerals, but the exact mixture remains uncertain. Understanding the composition of the dark material would provide clues about its origin and the processes that have modified it over time. It might also reveal connections to other dark materials found elsewhere in the solar system, such as on the surfaces of comets and primitive asteroids. The internal structure of Iapetus is poorly constrained by current observations. We know that the Moon is composed primarily of water ice, with a small rocky core, but the exact proportions and the detailed structure of the interior remain uncertain. Future missions with more precise gravity measurements might be able to map the internal structure in greater detail, revealing whether there are any surprises hidden beneath the icy surface. The age of various features on Iapetus is another area of uncertainty. Crater counting provides estimates of surface ages, but these estimates depend on assumptions about the rate of impacts over time, assumptions that may not be accurate for the outer solar system. The age of the equatorial ridge, the age of the dichotomy, and the ages of individual craters and basins all remain subjects of debate and investigation. The oddness of Iapetus has occasionally led to speculation that it may be an artificial construction by extraterrestrials. While this idea makes for entertaining science fiction, there is no scientific evidence to support it. All of the features observed on Iapetus can be explained by natural processes, even if we do not yet fully understand all of those processes. The strangeness of Iapetus is a testament to the creativity of nature, not evidence of alien engineering. As you rest and let your mind drift, consider the nature of scientific inquiry. The mysteries of Iapetus are not frustrations but invitations, opportunities for future scientists to make new discoveries and advance our understanding of the universe. Every unanswered question is a door waiting to be opened, a path leading to new knowledge and new wonders. The scientists who study Iapetus today are part of a tradition stretching back to Giovanni Cassini, a tradition of curiosity and investigation that has brought us from flickering candlelight to robotic spacecraft exploring the outer solar system. The mysteries of Iapetus remind us that the universe is vast and complex, full of phenomena that challenge our understanding and force us to think in new ways. This is the joy of science, the thrill of confronting the unknown and slowly, patiently, piece by piece, building a picture of how the universe works. Iapetus has been a teacher for more than 3 centuries, and it has many lessons still to share with those who are willing to learn. Chapter 11, Iapetus in Human Culture and Imagination. Throughout human history, the objects in the night sky have inspired stories, myths, and dreams that connect us to the cosmos and to each other. People used to put their stories in the skies with shamans and night watchers, coming to know the celestial realm, noticing changes like planetary movement, the sun, moon, and such, and seeking meaning in what they saw. Iapetus, though invisible to the naked eye and unknown to ancient stargazers, has nonetheless found its place in this tradition of cosmic storytelling, inspiring writers, artists, and dreamers since its discovery more than 3 centuries ago. The very name of this moon connects it to one of humanity's oldest and most enduring mythological traditions. In Greek mythology, Iapetus was one of the 12 Titans, the primordial deities who ruled the cosmos before being overthrown by the Olympian gods led by Zeus. Iapetus was the son of Uranus, the sky, and Gaia, the earth, making him a child of the 2 most fundamental elements of the ancient Greek universe. He was the father of 4 sons who played crucial roles in Greek mythology: Atlas, who was condemned to hold up the sky; Prometheus, who stole fire from the gods and gave it to humanity; Epimetheus, who accepted Pandora and her fateful box, and Menoetius, who was struck down by Zeus for his hubris. The choice of this name for Saturn's third largest moon was made by John Herschel, the son of William Herschel, who discovered Uranus. In 1847, John Herschel proposed that the moons of Saturn should be named after the Titans, the brothers and sisters of Cronus, who was the Greek equivalent of the Roman god Saturn. This naming convention connected the Saturnian system to the rich tradition of Greek mythology, giving each moon a story and a personality drawn from ancient legend. The connection between Iapetus the Titan and Iapetus the moon is more than just a name. In some versions of the myth, Iapetus was associated with mortality in the west, the direction of the setting sun, and the realm of the dead. This association with darkness and endings seems almost prophetically appropriate for a moon with one hemisphere as dark as night. The ancient Greeks could never have known that a world bearing this name would one day be discovered, a world divided between light and shadow, but the resonance between the myth and the reality adds a layer of meaning to our exploration of this distant moon. As long as human beings have existed, they have certainly wondered at the sky. This wonder has driven us to explore, to question, to seek understanding of the cosmos that surrounds us. Iapetus represents one small piece of this vast cosmic puzzle, a world that has captured human imagination and inspired us to reach beyond our own planet in search of knowledge and wonder. The modern cultural significance of Iapetus owes much to the work of science fiction writers, who have used this moon as a setting for stories that explore themes of mystery, discovery, and the unknown. The most famous of these works is undoubtedly Arthur C. Clarke's novel 2001: A Space Odyssey, published in 1968. In Clarke's story, Iapetus plays a crucial role as the location of a massive alien artifact, a monolith placed there by an advanced extraterrestrial civilization millions of years ago. Clarke chose Iapetus as the site of his monolith precisely because of the moon's mysterious nature. The dramatic brightness dichotomy, which was known but not understood at the time Clarke was writing, suggested to him that something unusual might be happening on this distant world. In the novel, the bright region of Iapetus is revealed to be artificial, a vast white plain created by the aliens as a marker or signal. The protagonist of the story, David Bowman, travels to Iapetus and discovers the monolith, which serves as a gateway to a journey across the cosmos. The film version of 2001: A Space Odyssey, directed by Stanley Kubrick and released the same year as the novel, changed the location of the final monolith from Iapetus to Jupiter orbit, primarily for practical reasons related to the visual effects available at the time. But Clarke's original vision of Iapetus as a world of mystery and alien contact has persisted in the popular imagination, influencing how many people think about this moon and its place in the solar system. Clarke returned to Iapetus in his later novels, including 2010 Odyssey 2 and subsequent books in the series. In these works he continued to explore the idea of Iapetus as a world touched by alien intelligence, a place where humanity might find evidence of other minds in the universe. While these stories are fiction, they reflect a genuine sense of wonder about Iapetus and its mysteries, a wonder that is shared by scientists and dreamers alike. Other science fiction writers have also been drawn to Iapetus as a setting for their stories. The moon's unusual features, its two-toned surface, its equatorial ridge, its distant orbit around Saturn, provide rich material for imaginative exploration. Stories set on Iapetus often play with the contrast between the dark and bright hemispheres, using this visual dichotomy as a metaphor for themes of duality, hidden knowledge, and the boundary between the known and the unknown. The naming of features on Iapetus reflects another aspect of human culture, the medieval French epic known as the Song of Roland. This poem, composed in the 11th century, tells the story of the Battle of Roncevaux Pass, in which the rearguard of Charlemagne's army was ambushed and destroyed by Basque forces. The hero of the poem, Roland, refuses to call for help until it is too late, and he dies along with his companions in a last stand that has become legendary in European literature. The International Astronomical Union, which is responsible for naming features on planets and moons, chose the Song of Roland as the naming theme for Iapetus. As a result, the craters, mountains, and regions of this moon bear names drawn from the poem: Charlemagne, Roland, Oliver, Turpin, Balagunt, and many others. The bright trailing hemisphere is named Roncevaux Terra, after the pass where the battle took place, while individual features carry the names of characters from the epic. This naming convention creates a strange and beautiful connection between a medieval poem and a distant frozen world. When scientists discuss the geology of Iapetus, they speak of Charlemagne crater and Roland crater, of the mountains of Roncevaux Terra and the dark plains of Cassini Regio. The heroes and villains of an 11th century epic have been transported across nearly 1 billion miles of space, their names now attached to features that will endure for billions of years. In this way, human culture reaches out to touch the cosmos, leaving its mark on worlds that no human has ever visited. If you study the constellations, you're really studying a culture, because early people would incorporate their mythology into these sky pictures, with each one telling a story from which you can learn about the people who wrote those stories. The same is true of the names we give to features on other worlds. The names on Iapetus tell us about our own culture, our love of epic stories and heroic deeds, our desire to find meaning and narrative in the universe around us. Literature, in all its forms, captures the eternal ebb and flow of the human spirit, reminding us of where we have been and hinting at where we might go next. The stories we tell about Iapetus, whether scientific papers or science fiction novels, are part of this great tradition of human storytelling. They connect us to the cosmos and to each other, weaving a narrative that spans from ancient mythology to modern space exploration. The visual appearance of Iapetus has also inspired artists and illustrators who have attempted to capture the strange beauty of this two-faced moon. Paintings and digital renderings of Iapetus often emphasize the dramatic contrast between the dark and bright hemispheres, showing a world divided between shadow and light. The equatorial ridge with its towering peaks provides another striking visual element, a mountain range unlike anything found on Earth. These artistic representations serve an important function in communicating the wonder of Iapetus to the general public. Most people will never have the opportunity to study the scientific data from the Cassini mission, but they can appreciate a beautiful image of this distant moon. Art bridges the gap between scientific knowledge and public understanding, making the wonders of the solar system accessible to everyone. The cultural significance of Iapetus extends beyond fiction and art to include its role in scientific education. This moon is often used as an example in astronomy courses and popular science writing, illustrating concepts such as tidal locking, thermal segregation, and the diversity of worlds in the outer solar system. The dramatic visual appearance of Iapetus makes it an effective teaching tool, capturing students' attention and sparking their curiosity about planetary science. As you rest and let your mind wander, consider the many ways that Iapetus has touched human culture, from the ancient myths of the Titans to the science fiction visions of Arthur C. Clarke, from the medieval epic of Roland to the scientific papers of modern researchers. This moon has inspired stories and dreams across the centuries. It is a reminder that the exploration of space is not just a scientific endeavour, but also a cultural one, a way of extending human meaning and imagination into the cosmos. The story of Iapetus is, in many ways, the story of human curiosity. It begins with Giovanni Cassini peering through his telescope in 1671, wondering why his newly discovered moon seemed to disappear on one side of Saturn. It continues through centuries of observation and speculation, as astronomers struggle to understand the strange brightness variations they observed. It reaches a climax with the Cassini spacecraft, sending back images that revealed the true nature of this remarkable world. And it continues today, as scientists analyse data and propose theories, as writers imagine stories set on this distant moon, as artists create images that capture its alien beauty. In the vast expanse of a deep velvety night, when the first storytellers painted tales with their words, there was a magic at play, a magic that would stand the test of time and resonate across civilizations. That same magic is at work when we contemplate Iapetus, a world so distant that its light takes more than an hour to reach us, yet so vivid in our imagination that it feels almost close enough to touch. This is the power of human curiosity and creativity, the ability to reach across the void of space and make distant worlds our own. Chapter 12. The Future of Iapetus Exploration. As we approach the conclusion of our journey through the story of Iapetus, let us turn our gaze toward the future and consider what new discoveries might await us in the years and decades to come. The exploration of this remarkable moon is far from complete, and there is much that we still do not understand about its origin, its evolution, and its place in the broader story of the solar system. The Cassini mission, which ended in September 2017, provided a wealth of data about Iapetus that scientists are still analysing. New discoveries continue to emerge from this dataset as researchers apply new techniques and ask new questions of the observations that Cassini collected. The images, spectra, and other measurements from Cassini will remain a valuable resource for decades to come, supporting scientific investigations long after the spacecraft itself has been destroyed. But there are limits to what can be learned from the Cassini data. The spacecraft made only a few close approaches to Iapetus, and there are many areas of the surface that were not imaged at high resolution. The composition of the dark material remains uncertain, and the internal structure of the moon is poorly constrained. To answer the many questions that remain about Iapetus, new missions will be needed, missions that can study this moon in greater detail than was possible with Cassini. Several concepts for future missions to the Saturnian system have been proposed, though none have yet been approved for development. These concepts range from orbiters that would study Saturn and its moons from a distance to dedicated missions that would focus specifically on one or more of the most interesting moons. Iapetus, with its unique features and many mysteries, is often mentioned as a potential target for future exploration. One possibility is a dedicated orbiter that would enter orbit around Iapetus and study it in detail over an extended period. Such a mission could map the entire surface at high resolution, measure the composition of the dark and bright materials with precision, and determine the internal structure of the moon through gravity measurements and other techniques. An orbiter could also study the interaction between Iapetus and the Phoebe ring, observing the ongoing deposition of dark material on the leading hemisphere. An even more ambitious possibility is a lander that would touch down on the surface of Iapetus and study it directly. A lander could analyse the composition of the surface materials with instruments that are impossible to use from orbit, determining the exact mixture of organic compounds, minerals, and ice that make up the dark and bright regions. It could measure the physical properties of the surface, such as its hardness, porosity, and thermal conductivity, and it could search for any signs of geological activity, however unlikely, that might indicate ongoing processes beneath the frozen surface. The challenges of sending a mission to Iapetus are significant. The Moon is nearly 1 billion miles from Earth, requiring years of travel time even with the most efficient trajectories. The communication delay between Earth and Iapetus is more than an hour each way, making real-time control of a spacecraft impossible. The extreme cold of the outer solar system poses challenges for spacecraft systems, requiring careful thermal management to keep instruments and electronics functioning. And the limited sunlight at Saturn's distance makes solar power impractical, requiring the use of nuclear power sources that are expensive and politically sensitive. Despite these challenges, the scientific rewards of exploring Iapetus would be substantial. This moon offers a unique window into the processes that have shaped the outer solar system, from the formation of icy bodies in the solar nebula to the ongoing interactions between moons, rings, and debris. Understanding Iapetus would help us understand the broader population of icy worlds in the outer solar system, including the dwarf planets and other objects of the Kuiper belt. The equatorial ridge of Iapetus is particularly intriguing as a target for future exploration. Understanding how this feature formed would provide insights into the early history of the Moon and the processes that have shaped icy bodies throughout the solar system. A detailed study of the ridge, including its structure, composition, and age, could help distinguish between the various theories that have been proposed for its origin. The dichotomy between Cassini Regio and Roncevaux Terra is another priority for future investigation. While the basic mechanism of thermal segregation is understood, many details remain uncertain. How thick is the dark coating in different areas? What is the exact composition of the dark material? How has the dichotomy evolved over time? Answering these questions would require detailed observations that go beyond what Cassini was able to provide. The possibility of exploring Iapetus with human astronauts lies far in the future, if it ever becomes reality at all. The distances involved, the harsh environment, and the technical challenges of human spaceflight to the outer solar system make such a mission extremely difficult. But it is not impossible to imagine a future in which human beings stand on the surface of Iapetus, looking up at the ringed wonder of Saturn hanging in the black sky, walking across landscapes that have remained unchanged for billions of years. For now, our exploration of Iapetus must continue through robotic proxies, spacecraft that carry our instruments, and our curiosity to distant worlds while we remain safely on Earth. These robotic explorers are extensions of ourselves, our eyes and hands in the cosmos, allowing us to experience the wonders of the solar system, even though we cannot travel there in person. The data they return becomes part of our collective knowledge, shared among scientists and the public alike, enriching our understanding of the universe we inhabit. As you rest and relax, consider the future that awaits Iapetus and those who study it. New missions may be launched, new discoveries may be made, new questions may be asked and answered. The story of Iapetus is not finished. It is still being written by scientists and engineers, by dreamers and explorers, by all those who look up at the night sky and wonder what mysteries might be waiting to be found. The exploration of space is a multi-generational endeavour, a project that spans lifetimes and connects us to both our ancestors and our descendants. Giovanni Cassini, peering through his telescope in 1671, could not have imagined the spacecraft that would one day bear his name, travelling across the solar system to photograph the moon he discovered. We, in turn, cannot imagine what future generations will discover about Iapetus, what new technologies they will develop, what new questions they will ask. But we can be confident that the exploration will continue, driven by the same curiosity that has motivated human beings, since we first looked up at the stars and wondered what they were.